Hey, Dr. Clark with you again for the capstone of the calculus. That's right, it's the divergence theorem. Can you believe it? I can. Let's get started. So the divergence theorem, this really is the capstone of the course. I think you're going to find it very exciting. To get us started, let's remember Green's theorem flux addition. So remember Green's theorem, we had a curve, right? Inside the curve, and it was a simple closed curve. Inside that simple closed curve, we've got a region R here. And then on top of all that, you've got this green vector field F, right? So you've got some vector field, the wind is blowing or the water is flowing or whatever it is. And then what we're going to do along that curve, at each point, we're going to look at the normal vector. And we're going to dot product the F vector with the normal vector. And in this case, they're sort of pointing mostly in the same direction. So when you do that dot product, F dot n, that's going to give you a positive number, which is saying that that vector field is flowing out of the region right there. Over here, you can see that the vector field is orthogonal to the normal direction. And so when you dot product these vectors, you're going to get 0. Here, the flow is neither into nor out of the region. It's just sort of circulating around. So this is all circulation but no flux. This is mostly flux, a little bit of counterclockwise, or clockwise circulation here. Here you've got a lot of, but this would be like negative flux coming in, etc. All right, so this line integral is going to add up all the way around all those fluxes and tell you what's the net flux. Okay, and what Green's theorem said was, hey, we don't want to do that line integral. Let's instead do an integral on the inside of the region. Right? So these things are two completely different integrals, but they're equal to the same thing. And what do you integrate? Well, you integrate this px plus qy, which is known as the divergence of the vector field. It tells you inside how much the vector field is sort of accelerating or expanding, if there's any sources of flux or sort of sinks of flux, right? And if you add all those divergences up for the whole region, that's the same as seeing how much got out the outside. Okay, now that's Green's theorem flux. We've already seen that. That's 2 dimensions. What the divergence theorem does is it just takes that and upgrades it into 3 dimensions. So in 3 dimensions, you'd have a solid region D with a surface around it here. So you've got some surface. And then if you do F dot n, that's just the flux out of the surface, right? So F dot n is the flux coming out of the surface. That's a surface integral. And it gives you the net flux. So how much, water is flowing through the net or wind is blowing or whatever it is, right? And you can see here again, that looks like positive flux. Here looks like 0 flux because the vector field is orthogonal to that normal vector, right? So you're going to add those all up. Some are positive, some are negative, some are 0, and you get the total flux. Well, the divergence theorem says just add up the divergences on the inside, right? Just integrate the divergence. So Green's theorem, you just integrated the divergence, but it was a 2-dimensional region. Divergence theorem, you just integrate the divergence, but it's a 3-dimensional region, so you get a triple line integral. And the divergence is px, qy, rz. Notice it's 3 dimensions, so we have the rz here. In 2 dimensions, we just had the vector field pq. Other than that, it's the same exact idea as Green's theorem in 2 dimensions. All right, and then just couple other, little tiny ideas that you can add into it. Could you relate a solid region's volume to an integral on its surface? Well, we've done this before with Green's theorem using area and the line integral. Well, we're doing the same thing. Take, for example, the vector field x, 0, 0. If you took the divergence of that vector field, you'd get, well, the x derivative of x is 1, and then the y derivative of 0 is 0, and the z derivative of 0 is 0, so that's just 1. Well, integrating 1 on the volume gives you the volume, right? But that's the same as the divergence of that vector field, which means that the flux of this vector field through the surface is equal to the volume. So that's kind of cool. You can actually evaluate the volume of a region inside by calculating the flux of the vector field x, 0, 0 on the surface. Of course, you could do 0, y, 0 or 0, 0, z. Any of those would work. And you'd get the same thing. So that's kind of cool. You can actually compute the volume by knowing something about the surface area. Another little tidbit here is if the region is hollow, let's say this is like an egg minus the yolk here. So you've got an egg here, you took the yolk out. So the region is just this blue solid here. Well, the normal vector would point out here, but on the inside it would sort of point in. Okay, so you want the sort of the inward pointing normal vector here, but the outward pointing normal vector here. If you did the divergence theorem, it would just turn out to be you could integrate the divergence on that hollow solid region. You'd have to do two surface integrals, one for this outside surface where n is pointing out, and then one for this inside surface where n is pointing in. But the sum of those two surface integrals, those two flux surface integrals, would equal the integral of the divergence on that in between region there. And then sometimes you can use this to evaluate difficult surface integrals by splitting the surface into parts. So let's say you maybe you could do the outside surface, that was easy. The inside surface was hard, but you could do the volume. Well, you know the integral of the divergence is equal to the sum of those two surface integrals. So if you can do, so that's three things, 1 plus 2 equals 3. If you can do any two of them, then you can solve for the other one. So sometimes you can evaluate difficult surface integrals by splitting the surface into parts. Using the divergence theorem, that's going to equal the sum of the surface integrals, and then you subtract over the ones you can do, and the net is the one you can't do. So that is the divergence theorem in a nutshell. It's basically just the flux-Green's theorem upgraded into 3 dimensions. You integrate the divergence, you get the net flux. That one idea works both for a two-dimensional region with the line integral curve, or a three-dimensional solid region with a surface integral on the outside. And that's called the divergence theorem. In the next video, we'll see some examples, so I'll see you there.